Alright, let's do some more multiplication. Here we're multiplying a polynomial times a polynomial. Well, in this first example you can see it's a binomial times a trinomial. And because we learned how to do this without using the FOIL method, there's nothing new we need to learn here. We just keep doing the same sort of thing. We're going to take each term in the first times each term in the second. 2x times x squared is 2x cubed. 2x times 5x, 2 times 5 is 10. X times x is x squared. 2x times negative 1 is negative 2x. Okay, I'm done distributing my 2x. Now I'll move on to my 3. 3 times x squared is 3x squared. 3 times 5x is 15x. And 3 times negative 1 is negative 3. So now I do need to combine like terms. You'll notice things don't line up perfectly, but it works out pretty well, actually. The x squared terms are there and there. We can combine those to get 13x squared. The negative 2x and the negative 5x, those are my linear terms, those degree 1. We get 13x. And the only one I haven't yet taken into account is the negative 3, so I'll tack it on there. So this pattern that I'm doing, I'm starting off with the highest degree term and then working down. So degree 3, degree 2, degree 1, degree 0. This, not only does it put this into standard form, when I add these together, it also makes sure that I'm including everything. Now, I'm also kind of making sure I'm including everything by doing these underline things that I'm doing. But, you know, that's just how I'm doing it right now. I don't generally do it that way, but sometimes I do. Alright, so let's simplify this expression. X times x squared is x cubed. X times 2xy is 2x squared y. And x times y squared is xy squared. It is important that you put the square in the correct place. This one says I have 2 copies of the x, this one says I have 2 copies of the y. So notice these are not like terms. Alright, next I'll move on. I'll distribute my opposite of y. So the opposite of y gives me the opposite of x squared y. Y times x squared, or x squared times y, with the negative in there. The opposite of y times 2xy is a negative 2xy squared. I have the negative times the 2, that's a negative 2. I have an x, and I have a y times y, which is y squared. Alright, and then I have, distribute to this last term, the opposite of y times y squared. This is negative y cubed. Alright, it looks like every single term here is degree 3. So I'm just going to start off with ones that are purely x's. So I get x cubed. Next I'm going to do all the ones that have 2 x's and a y. So there's that one and that one. So 2x squared y and minus x squared y. This will be plus x squared y. Then I'll do the ones that have 1 x and 2 y's. We have a positive 1 and a negative 2, so this is minus xy squared. And then my last term is minus y cubed. It's kind of interesting once you start doing these, putting it into standard form. You'll notice that the x's kind of fade out as we go along here. There's 3 x's, then 2, then 1, then 0, while the y's fade in. We have 1 y, or 0 y's, then 1, then 2, then 3. Overall, we have 3 variables on each of these, but it's the x's fading out as the y is fading in that allows it to kind of stay in alphabetical order. Alright, for this example, we have, it looks like there are 3 different things that we're multiplying together. We have a 2x, an x minus 4, and a 3x minus 5. Let's just review a quick basic multiplication. If we had 2 times 3 times 4, and we wanted to multiply these together, we don't multiply everything multiple different ways. What we do is we pick and we say, okay, I'm going to do these first. I'm going to do 2 times 3, which is 6, and 6 times 4, which is 24. So you kind of pair them off. And that's what I would do here. You could choose to pair off these two. You could do that. Or you could choose to pair off those two. It actually doesn't matter. That's the associative property that's allowing me to kind of pick and choose how I'm pairing them off. I'm actually going to choose to do it this way, because then I'm doing a binomial times a binomial first, and I get that 2x out in the front. So that's how I'm going to do it here. So taking these binomials multiplied by each other, x times 3x is 3x squared. X times negative 5 is a negative 5x. Now I'll distribute my negative 4. Negative 4 times 3x is negative 12x. and then negative 4 times negative 5 is a positive 20. And I'm actually going to take a moment and clean up the insides of these brackets. 3x squared. These two middle terms combine to give me a negative 17x. Now I can distribute my 2x through the parentheses, rather. So 2x times 3x squared is 6x cubed. 2x times negative 17x is negative 34x. And 2x squared. 2x times 20 is plus 40x. This is in standard form. There's a degree 3, degree 2, degree 1. So I'm happy with that. And the last example we'll see on this page, we take x plus 2 quantity cubed. Now, we've seen how to do squares. We've seen how to do x plus 2 quantity squared, if it was like that. This is x plus 2 quantity cubed. We haven't seen any special rules for here. And be careful not to be tempted to just distribute this 3 through here, because that's not the same thing. That's not what's going to happen here. This needs to be x plus 2 times x plus 2 times x plus 2, because it's taking it cubed. Remember, if you're tempted to use that rule of exponents, or if you're still looking at that and trying to figure out why you can't use it, the rule of exponents you're trying to use looks like this. A to the r times b to the r, or ab to the r, rather, is a to the r times b to the r. This is multiplication on the inside of the parentheses. We say we're distributing exponents over multiplication, and that this works because exponents are repeated multiplication. In general, if you try to do it like this, this is not going to be the same thing as a to the r plus b to the r. This is not the same thing. You can't distribute exponents over addition like this because exponents are not repeated addition. You don't have that same sort of pattern happening here. So that's why you can't do it this way. But you can do it with multiplication. Unfortunately, we have addition here, so we can't do it. Alright, so what I can do, though, is I recognize if I take two of these, that is a difference, or a sum squared. So I can go ahead and apply my special product here. This would be x squared plus 4x plus 4. So it's the first term squared plus 2 times the product of the two terms, so 2 times x times 2, which is 4x, plus the second term squared. That's the 4 there. Now, however, I have a trinomial times a binomial, so now I can just go ahead and do the same thing I was doing up here. I'm going to take each term in the first parentheses times each term in the second. So x squared times x is x cubed. X squared times 2 is 2x squared. 4x times x is 4x squared. 4x times 2 is 8x. 4 times x is 4x, and 4 times 2 is 8. This gives us x squared, x cubed rather. Oh, that's big. X cubed plus, combining these, we get 6x squared plus 12x plus 8. If you're interested, this is not something, this is something that's extra. This is not part of the class. There's something called the binomial theorem. And the binomial theorem works like this. If we have a plus b, and we're raising it to some generic power n, it gives us a way of expanding this out. This ends up using something called combinations. If you talk about, you'll talk about combinations in the other in Math 115 rather. But in general, if you were to take, well, actually, let me express it this way. Let's do with Pascal's triangle. So Pascal's triangle is just kind of a pattern that you can create. So I'm creating a triangle, and each term, each number I'm writing here is going to be summing the numbers that are above and to the left and above and to the right. So this 1, there's nothing above and to the left, but there's a 1 above and to the right. This one right here is a 1. Once I get in here, it starts getting more interesting. 1 plus 2 is 3. 2 plus 1 is 3. And so on. We get 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And I could keep going with this as long as I'd like. So the binomial theorem basically says, if I call this the row 1, 0, row 1, row 2, and so on, if I was to take the nth row, let's do, this is row 4. If I was to take this, this would tell me how this would expand. If I had a plus b to the 4th power, these are the coefficients that I would end up getting. I would get a to the 4th plus, well, first off, I'm just going to do this kind of thing. We saw this before. The a's fade out as the b's fade in. A, b cubed, and b to the 4th. You can see 4, 3, 2, 1 for the a's, 0, 1, 2, 3, 4 for the b's. But there's going to be several different instances of these happening, so we need to read off our coefficients from Pascal's triangle. We get 1a to the 4th plus 4a cubed b plus 6a squared b squared, 4, 1. So this a plus b quantity to the 4th actually expands out to be this mess. And this Pascal's triangle is useful because it's easy to see what the coefficients of each of these terms should end up being after we expand them out. If we're talking about a plus b to the nth power, we would take row n and whatever ends up being there. The reason I mentioned Math 115 is these numbers actually end up, you can express these using something called a combination. This is 5 choose 0, this is 5 choose 1, this is 5 choose 2, this is 5 choose 3, 5 choose 4, and 5 choose 5. That's what these numbers are. So you can express this out using combinations, and it's a expanding these out without the binomial theorem is extremely easy to make a mistake on. Oops, I guess you couldn't see what I finished there. 5 choose 5 there. Expanding this out without the binomial theorem is just kind of infeasible. It's hard to do, and it's easy to make mistakes on. So this binomial theorem is quite useful if we have a binomial and we're raising it to a power. Now the reason I'm bringing this up right now is because if you see a binomial in this class and it's raised to a power, well, most of the times in this class you're going to be seeing it squared, but that's one of our special products. The only other times you're really going to be dealing with this is if you have a cube. If you see a 4 as the exponent there, well, you'd have to do either use the binomial theorem, or you'd have to end up doing this a plus b times a plus b times a plus b times a plus b, and then distributing each of those out. And you can see there's quite a bit involved with this. Eventually you would end up getting that thing right there, though.